بسم الله الرحمن الرحیم ولا حول ولا قوة الا بالله العلی العظیم حسبنا الله و نعم الوکیل نعم المولا و نعم النصیر. Last session we talked about the preliminaries of dynamic analysis of serial manipulators. And we saw that screw axis is a very good representation for angular velocity, since the angular velocity of angular acceleration of a rigid body is also along the same old screw axis where the angular velocity and the rotational position was aligned to. And also we talk about the center of mass. Center of mass is also very important. We notice it very clearly here. And some notes about the inertia matrix or moment of inertia that is usually given to you. We consider it as known, but how to treat that and how this comes into the picture. This comes into the picture for defining the kinetic energy of the system, that we will use that in Lagrange formulation. In this session, I will give a motivating example how the Lagrange method can be applied for a simple, not very simple, but simple case, and then I will give the generalized coordinate and generalize the representation of the Lagrange formulation, and then with some examples and also some programs, written programs in MATLAB, you can use that. And again, I mentioned to you that in this course you are up to use different MATLAB or Maple programs for your assignment, and these are very important because the exams would be very similar to the assignment that you have doing. Of course, not the same robot, some other robot, but the same approach that we are learning through the assignment, we will continue in the exam. So if you have your own exam written, of course, you might not use my exam or the TA exam, but you should write your own exam or your program in MATLAB that you can use that in the exam, hopefully. Now, let's go through the motivating example. I consider a system with 2 degrees of freedom. We have 2 mass here, one mass here as a pendulum, which is rotating about this axis, and one mass here, which we consider it a point mass, a pointwise mass, which is have a translating motion about or along this axis. So we have a phi rotation of the this pendulum, and also a r, we call it r, a distance that the movement of this mass. Of course, this mass is also sprung. It is not a usual mass, it is a sprung mass which has a spring here to have the oscillation also coming into account. This example gives you very good intuition how the Lagrange is used, and compared to other methods like Newton-Euler method that require the acceleration and many different internal forces to be found, Lagrange is quite straightforward and we can go it through that way. So consider that the length of the this pendulum is L, and the center of mass is somehow in the middle, but we consider it as H, the distance of the center of mass here, and we consider that this large ball has a mass of m and a moment of inertia matrix, which is called by I. Of course, we are considering a planar motion, and if we are using a planar motion, only IZZ along the z-axis, if this is x and y-axis, along the z-axis is considered here. and the spring stiffness is K, and this small mass, or the point-wise mass here, we consider it with small m as the mass of the system. And finally, we have considered that the gravity is in this direction, in y direction, or in minus y direction. We have x and y here. Or if we have x and y direction in this here, g is along y direction. And we have a input torque or a motor just on this joint. We don't have any motor here. This is just sprung. But here we have a torque applied to the system. Now, if we consider that with this detail, and we have to find, let's say, 3 steps. The 3 steps are given here. The 3 first step, we should find the generalized coordinate, and these are very simple in robotics because we have defined already generalized forces and generalized motion as a twist or as a translation and orientation. Here we call it a generalized coordinate. We call the coordinate the minimum number of coordinates that are independent to each other, and basically define the motion of all the different bodies of the system. But why we call it generalized? Because this motion could be either a rotational motion like phi or phi here, as we see, or a translational motion like R, like what we have in revolute and prismatic joint. So here we consider the 2 generalized coordinate. We considered Q as before. This Q is the vector of generalized coordinates now here. The first one is rotation and the second one is translation. It is quite clear that we have 2 masses, so 2 generalized coordinates could be used in here. Usually the same old David-Hartenberg prop assignment that we have in the general robot. As we find the generalized coordinate, which is quite simple, the next step is the generalized forces. The generalized forces are the external forces. The external forces acting on the system except the gravity. We consider the gravity separately. Except any spring or elastic deformation that we have. We consider that also separately. We have also here, as you see, we have gravity and spring. We don't consider that. We consider the external forces that are applied either by the motors and or on this particular coordinates at each particular coordinate, or maybe some disturbance forces, some even the frictions we consider that somehow separately. They are considered in here, but we consider it separately if we have some friction at the joints or at the motion. But these 2 are along the Q, the big Q, the generalized forces. We call it generalized. Why? Because the generalized force is denoted for both forces and torques, and we don't consider that separately or differently. We consider that all in one vector. As you see, we have a rotation here. Along this rotation, what is the external force that is applied here? Is this the motor torque that we are applying here? So this would be tau. And what about here? If there is any friction or anything, then there is some forces. But if there is no friction, we consider that there is no friction at this example, at this simple example. There is no external forces or any motor moving, providing some motion here. Therefore, by this means, we have also the force here equal to 0. So if you find the Q, you can find the Q, the big Q. Of course, in a very long general description, maybe we need to use the virtual work approach to find the Qs, but in the robotic application, it is quite easy, and you find it is usually the torques and the forces that we have at each joint, at each actuated joint considered in here. After defining these two, we should find the Lagrangian. The Lagrange approach is based on Lagrangian. And Lagrangian has two components. Lagrangian with the script L is defined by kinetic energy of the total system minus potential energy of the system. And that's why in the last part of the last sentence of our previous session, we just defined the kinetic energy of for a general motion. What is the kinetic energy? For the planar case, it is quite simple. It is the kinetic energy is considered of two parts: the translational motion and the angular motion. So we consider for each joint, for each body, each rigid body, we have here two bodies, big M and large M and small m. We have two bodies. For each of that bodies, we consider 1/2 mvc squared. We have half mv squared as the kinetic energy. You are quite familiar with that. But which velocity of which point? Velocity of the center of mass. Very, very important. Velocity of the center of mass. And we know that K is a scalar. It is not a vector, because this VC is VC transpose VC. VC squared is a dot product of VC, so it is quite scalar. And we have also 1/2 I omega squared. If we have some rotational motion that we are watching that we have here, the same, very similar to 1/2 mv squared. We have 1/2 I, but again, which I? The I is the moment of about center of mass, not about here, not about there, just the moment of inertia about center of mass of each point of each rigid body that we have. We have a center of mass here, so we should find the I with respect to this point, and this should be either given to you or you find it by the topic that we discussed last time. So as simple as that. And the most difficult part in this formulation is to find exactly what is the velocity of VC of mass and the angular velocity or of the rigid bodies. And since we have a very good last chapter about Jacobians, we have already found that for the end effector. So we use a very similar approach to find this general term. I will give it to you later. But here in this example, we can very simply find the center of mass velocity and use it in here. What about the potential energy? The potential energy is defined from other forces than the Q, the gravity force or some elastic forces that are present in this example. We call it very simple, mgh, the potential energy about one axis that you consider, one reference axis, how much height we have, the masses are going on direction of minus g. We call it mgh, or plus if there is some mass and gravity term here, and if there are some spring as here, any spring, if you have a linear spring 1/2 kx squared, and if you have some rotational spring, the same thing, 1/2 k rotational, and this x or delta x is delta theta, the angular motion that we have over there. Of the robotic manipulator, we don't consider the stiffness, and if, as you see, if there are some harmonic drives and something inside the system, then this could be considered as the elastic, as the kinetic energy by there. So by this means we have the kinetic energy and potential energy. We just subtract these two from each other and we find L. And this should be found for each mass rigid body of the system. Maybe the system is a multi-body system, a robot with 6 degree of freedom. It has 6 links, so we have 6 different parts. We should find each one of them one by one, these velocities and kinetic energy and potential energy. Then the rest can be done by Maple or by MATLAB. The deriving governing dynamic equation is found by this Lagrange equation or Lagrange formulation. This means that the first partial derivative, get the partial derivative of L with respect to each of the components of Q's. The Q is 1, 2 to M. Usually we have 6 degree of freedom in general, or 2 degree or 3 degree of freedom, so this could be different. For each Qi, where Q is basically this generalized coordinate that we have, we first get a partial differentiative with respect to Q dot I, and then differentiate it with respect to time. First partial differentiation, and then absolute differentiation with respect to time. And also minus partial differentiation of L with respect to Q. So the L, since as you see L is K and P, K is related to Q dot, usually we have V dot and omega dot to Q dot, and P is related to usually Q. Here you can see that this differentiation is done both on Q dot I and on Q dot I. And this is the component of generalized vector. So you have 2 masses or 2 generalized coordinates, you can find 2 dynamic equations. And these dynamic equations are second ordered systems. Since we have Q dot here, we are differentiating with respect to Q dot, we come to Q double dot, or the second derivative of the K, so we have the everything done in here. So we will do the treatment very exactly on the this example that we have, with 2 center of mass and the moment of inertia and so forth and so on. But if you would like to do it by just by intonation and some just intuition, then what we can do is we should make sure that the velocity, the only difficult part is this part. We should make sure that the velocities are found quite accurately and quite exactly as it is. So what we are doing, we can find it quite easily in this example. So we have 2 masses, and we find the velocity for the center of mass. This one and this one, angular velocity of this one and this one. Let's go to the linear velocity of VC1. If we have a pendulum motion here, the velocity would be r times omega, that we call h times omega, which is omega is phi dot, and the Vc would be this one. Vc squared would be h phi dot squared. So it is very simple. Vc is find the velocity of this Vc1. The first center of mass is found. What about the angular velocity of this rigid body? So the whole rigid body has the theta phi motion, so the angular velocity is phi dot. So this is the linear velocity squared, and this is the angular velocity. What about the second one? Here it has a bit more difficult motion, but not very difficult. This, as you see, since it is sliding along this and has also the rotational motion, you consider it y by 1, and you can consider that the velocity of the system, as you see, has a direction in this direction, very similar to hc, but with this length. We have a velocity in here, r phi dot squared. This is in this direction, and tangent. In this direction, in sliding direction, we have a r dot. We have a r dot here, and these two are perpendicular to each other at each position. So velocity squared for the second equation would be r dot squared plus r phi dot squared. We find the component of the velocity and do it by that. So we are using intuition here. For robotic manipulator, we do it, somehow more rigorously, and some definition. I will give it here later to you. And what about the omega of this case? So since these two are both moving on the phi dot, the omegas of both of them are equal to each other, so omega 2 is also phi dot. And so we have found the velocities quite accurately now. Now we go to the next step to find the total kinetic energy. We have two masses, we have two kinetic energy. The first kinetic energy, let's consider the pendulum one. As we saw, we have two parts. One part is 1/2 mv squared, that we have already found that, plus 1/2 I with respect to c, that we call it I here, phi square omega dot omega square, that here the omega square is phi dot squared. So very simple, 1/2 mvc squared plus 1/2 I with respect to c omega squared, and this is just found by that. But what about the second mass? Again, here there is two, it should be two kinetic energy component, but you see it only one. We have 1/2 mv squared, vc squared, plus there is another term, should be another term. It should be another term, 1/2 I omega squared. We have the omega of this case, but since we consider that this is a point mass, it is the very point-wise, doesn't have any extension in x and y direction. And there is no I. We considered no I here. So I is of I2 is equal to 0 here. Of course, we could consider also, if we would like to have more accurate, consider the I in here as well. But in this example, we consider that a point mass, and the I component is equal to 0. So everything is fine. Now we have three parts, and as you see, the kinetic energy is a function of phi dot or q dot and r dot in general, and as well as r and phi, if there are some r and phi, it could be possible to do that. Now, the potential energy on the other side would be the mass, how the mass is traveling along the y term. Since we have mgh, if we consider that, for example, if we consider that this is the reference of the potential energy, considering here, you can consider it everywhere. It is not a big important thing because you have only a offset there. If we consider potential energy equal to 0 here, so this the mass of this, we have mgh of where of the center of mass. Consider only the center of mass. How far it is from the center. If it is here, the reference is 0. It has along y-axis, there is a mgh cosine of phi in minus direction, because this is downward, not upward. We have not inverted pendulum, we have a regular pendulum here. So we have mgh cosine of phi with a minus sign for this case. And also we have, this one is very similar, mgr cosine of phi for this one. This is the r case. And we have also a spring here. Therefore, we should consider that also as well here. We consider that the spring is at rest when we are at R0, considering some place where the spring is just put there. So if the R0 is the unfolded spring, then we have 1 over 2k delta x squared, that here is r minus r0 squared of here it should be 2. This is a mistyping here, of course, r minus r0 to power 2 in here. I will correct that after the class, and finally if we can find the corrected version of the slides at the end of the sessions, at the day of the chapter. Now we have the k and we have the p here. We find the Lagrange equation as k minus p. And we just make some simplification. We brought all the phi terms all together here, and the r dot terms here. And then this 3 comes here, and this one comes here. And then we have also these 2 together, mh plus mr here. And this case here, we have 1, 2, 3, 4 part as RL. And the rest should be done either by hand, taking the derivative, or I suggest you to write a program for that. We have also some program. You can use our program or your program in symbolic MATLAB or in Maple to do the differentiation. So the rest is finding this differentiation. I do it in the next slide. I just copy that here for your reference to have the notation here. If L has the same 4 part, then we should find finding the derivatives just by 1 by 1, considering first Q1 as equal to Q. So we need to find the derivative with respect to phi dot, and then just make a derivative, do the derivative with respect to phi with minus sign, and then Q1. And everything is defined before. So we first find the derivative with respect to phi dot. As you see, this part comes out of here. The rest doesn't have phi dot. So this would be the part here. And then with respect to phi, we have only cosine of phi here. We find the derivative as this part, and Q1 in direction 1 is equal to tau. And the next step is just finding this derivative, and this derivative, since all of this part are quite constant, we have only phi double dot here. Of course, now R is also changing. This is not constant, so we have the derivative of that one coming into the picture here, and the rest could give us to this point. And the point is, this is a nonlinear equation. As you see, we have a multiplication of r dot phi dot in here, and also sine of phi in here. This is not a linear equation. This is a nonlinear equation. Second order, we have second derivative here with respect to your q's. And then this is the first equation. I make it black. This is the final value that we would like to find. And furthermore, we would like to also find with respect to r, we should find the same thing compared to r dot. This comes into the picture. And this one, with respect to r, we have this part and this part into the equation. and then making the derivative would give us these three terms done in here. And also this part comes into the picture as in this part, and then we have only three part in here with no external forces in there, no friction, no external forces. These two equations would be the governing dynamic equation that we have in here. If there is any question, it is quite easy. And you can do it. And this is defined for non-mechanical student. Usually mechanical student can are more familiar with Newton-Euler method, but you don't need to do that by Newton-Euler. If there is any question, please just speak up. If not, I will go to now general treatment. So now that we know how this should proceed, but we don't want to do it just case dependent, and we would like to find a general way to do that. And this is done by considering exactly it for a very specific manipulator that we have now, a robotic manipulator. So for robotic manipulator, Q's are very simple. Q's are either theta I for the revolute joint or di for the prismatic joint. The same old Dynamit-Hartenberg parameter that we had already, the variable, the variation there. What about the generalized forces? Very simple. There are either if we have revolute joint, compared to that, we have a torque actuator there. If we have a prismatic joint, we have a force actuator, a prismatic actuator. So if we have a force in here. So these can be found quite easily from the structure of the robot, just by a simple case. If we consider now, this is the external forces depending component with respect to the actuators. But there might be some other forces as well, and we have already discussed that in the Jacobian. If there are some wrench applied to the environment, if there is some torque or wrench applying, if the robot is applying a wrench, the Fe, to the environment, then the Jacobian Fe would be the map of that joint on each actuation forces. So we can add J transpose Fe to the robot as a Q, and if there are any friction forces, any type of friction, we usually consider viscous friction, but if there are some friction at each joint, we consider the joints, we don't consider other type of friction, then these frictions either is in torque friction or at force friction, depending on the revolute or prismatic joint. We consider we subtract that friction force from the tau I here, and then we have the translational or the rotational forces completely. And this gives us the generalized, and we call it generalized because we are including both the translational and rotational motion in here. Now, the Q, small q and the large q is fine. We can go to now finding the kinetic energy. And the kinetic energy, and then for the potential energy. I would like to use the same approach that we used in Jacobians, and you have already did some some experience, you have some experience and some assignment on the Jacobian, the first part of the Jacobian, and today is the deadline for your project, and I hope that you can finish that on time today. So you can see that we should do the same old case here. Here we have a generalized for a 3D manipulator, for a 3D motion. We have the translational velocity, kinetic energy, and angular velocity or angular kinetic energy. And this comes to 1/2 MIVCI. This is the velocity of center of mass of each link. And here is I with respect to C, I with respect to C, basically the moment of inertia of this with respect to the center of mass of the link that we would like to find. And then we should do it for each link and then just sum them up as the total kinetic energy. There should be considered a few points here. First, the velocity vectors and the moment of inertia could be expressed in any frame. This makes the intuition very simple. Why? Because we are just using the dot multiplication here, and this is scalar. So we can consider it into zero frame, into final frame, whichever which is easier for you to do that. And you remember that when we are finding the Jacobians, we could find the velocity with respect to any frame, any mid-frame or but in general, if there is no preference, we start with the zero frame and we find everything with respect to the zero frame as the general formulation. And also notice that if this usually the moment of inertia of the link is given with respect to its own frame. It is very hard to find this moment of inertia with respect to another frame. So it is with respect to its own frame. So this is usually I with respect to I is given as a constant number. But you can, if these omega i's are not in this frame, given, let's say, in zero frame or in any other frame, we can use the pure rotational map, the Ri to 0 that I explained last session. You can find it with respect to any center of mass with respect to zero frame if you would like to find this with respect to zero frame. So from I frame you can go to the zero frame, and we consider usually this I with respect to C. This is not I with respect to the frame C, but to the point C for the center of mass with respect to the zero frame, as you can see in here. You can find it in here. And what about the velocities? We can use the Jacobian, but a particular Jacobian, we call it a Jacobian JI. Since usually we use the Jacobian for the end effector or for the wrist. These were two particular points of interest in Jacobian analysis. Here, we need not the wrist or the end effector. We need the velocity of center of mass of each joint. You know, we have a number of joints, for a number of links. Center of mass of these links should be find the velocity. And we can use the same approach, but several times. We should find, we call the chi of the center of mass, the velocity and the angular velocity, the linear velocity and angular velocity as chi dot. And this is related to q dot with a Jacobian. We call it jj sub j sub I, j sub I. I means the ith link, the CI, the ith link, the center of mass of the ith link. And this Jacobian is particularly defined for the center of mass of each link. And we know that this is in general, it's a 6 by 6 frame, and you have a 6 by 1 Jacobian matrix in here, as you see in here, to find the G dot. So to finding a 6 by 1 here, if you have a 6 by 1 here, we need a 6 by 6 Jacobian to be defined in here. And this 6 by 6, the Jacobian, has two components. Some part, the top part was JVI, and some bottom part was J omega I. And you know that this was the screw axis, was exactly what we can find as the basis of the point at the screw. But the screw, the point of interest is not the end effector or not the wrist, is the center of mass of each link. So we did do the same treatment as we did there, but for the center of mass in here. They're exactly the same as before, but we have an index I or sub I in here. The sub I is representing for each link. Here is the final treatment, and the figure that I said, that first consider that we had a link, we had some screw axis or a J axis. There is no difference if you are happy or clear with the screw, you can go with the screw representation because they are the same thing, or you can go with the Z axis or then with Hartenberg representation. The same all this formulation are quite the same. The only difference is we should use the PCI star instead of using the PN star, the endpoint here. And PCI star, as you see, if each center of mass that you are considering for this particular Jacobian, we would like to find the 6 by 6 Jacobian for this point, exactly for this point, for all the links we should find these JIs. And these are, if the link is revolute, then the JVI would be this, the screw component, ZI cross PCI, where PCI star with respect to J minus 1 is basically can be found by this blue vector. This can be found for this vector, and then it can be propagated to the other one. I will do an exact explanation in the next slide. So if we can find the PCI, the position vector from the origin of J minus 1 link to center of mass of the link I, each proceeding or before joints, we need to find this, and we can do that iteratively. We can find the first one easy and then go back to the end one. As you see, this is PCI with respect to 0. And if we would like to find everything from the 0 frame, we need to find these vectors to be found in here. So finally, if you consider that exactly as what we did in chapter 4 and slide 21 for a conventional Jacobian, exactly just replace P star n to PCI with respect to 0 if you would like to find the velocity with respect to 0. And if you don't want to find from 0, you should treat to any frame J. You can have to any frame J. But we usually do it with respect to 0. This means that we should find this vector PCIs, as you can see in here. And if you have PCI with respect to 0, then you just do this multiplication, ZI cross that and ZI 0 to find the component of these two components of the Jacobian, and your Jacobian is find that way. Now, here you can see that we can do it component-wise and one by one or an iterative way. This is the final issue that we should get experience to that. For example, you're considering the link I, velocity of link I. Of course, if you would like to find the velocity of link I, all the motion of previous links are contributing to this velocity. So you have components to this point. But the motion of the after joints, the other joints that are after that point doesn't contribute in the velocity of that, if you are considering that. So when I would like to find the velocity of this point, how my wrist is moving doesn't contribute into that. The only preceding joints are providing the velocity. So this 6 by 6 Jacobian matrix that can be found by here, as you can see, can be divided by the columns. For example, for the very last point, all the columns are non-zero. But for the first joint, just the first Jacobian column is existing and the others are equal to 0. And this is the same for j omega y as well. So we go one by one to find these columns and then go forward to find this point. So we start with the first joint and find this one, and then we go to the second joint, and iteratively we can find all the Jacobians in here, which is basically given in the detail in the example, as you can see. It is not quite easy, not quite hard. The only thing is to find the PCIs and do this component-wise available. Now, if you have the Jacobians found, these Jacobians we have, the GVI and J omega I, the 6 by 6 or n by n Jacobians found, then the kinetic energy can be found in a general way. We have m1/2 mvc transpose vc omega I transpose I with respect to c omega I. And we know that the VCs, as you see in here, VCs and omega I, VCI and omega I are related to Jacobi, to Q, as with respect to Ji. And since we are finding the derivative with respect to Q dot, it is very, very good to represent it not in a large and open hand frame, just to represent it as the Jacobian frame. This is a revolutionary task that has been done by John Hollerbach maybe in 1986 or something at the beginning. So defining the VCs as Jacobians, VC Jacobian Q dot, VC transpose Q dot Jacobian. Then we can extract the Q and Q dot from this equation, and then we have JV transpose JV here, and J omega I transpose I J omega I, as we have in this formulation. And this will provide us the mass matrix. We can define the mass matrix. We can find the K as 1/2 Q dot transpose M of Q, the mass matrix, times Q dot, as the kinetic energy. This is the very, very important one. What would be the mass matrix? The same old thing that we have in here, that is derived by the Jacobian VIs. And you can see that by property, from physical property, that kinetic energy is a positive definite number, so the mass matrix shall be positive definite, and it should be and this is very important. If this is positive definite, it is invertible. We can use the inverse of mass matrix everywhere, not dependent on the configuration in the system. And the energy is also always positive, unless it is always positive. It could be 0 if the Q dot is equal to 0. So it is usually at the origin, at the 0 point, we have velocity 0. Otherwise, it is positive. We call also a strictly positive value for that. So we find a very important part of the Lagrange equation, and we will see that this will result into very important part of the dynamic equation, and everything is based on the Jacobians, and these are the most difficult part, or the most sophisticated or challenging part of finding the Jacobians, and you should do enough treatment about that and find to get well experienced on finding this. Now we go to the other part of the dynamic equation, which is called the potential energy or potential gravity function. The potential one is also find very, very systematically by multiplying the G matrix to PCI matrix. The same old PCI that we have before. We have found the PCIs here, you remember, PCI with respect to 0. If you would like to find everything with respect to 0, of course it could be any other as well, any other joint axis as well, but our treatment is with 0, 1. We consider MGH, the same old MGH that we have, but in a vector form. We say that consider the G vector, the gravity vector, as a vector. If it is along minus y direction, it is 0 minus G0. If we consider this direction maybe in any other frame, just consider the vector G. And if you have the vector G, then you can find the work that has been done. It would be minus mg PCI. The PCIs are the vectors that we are considering in these cases. The vector, the position vector of the center of mass that we have already used that to find the Jacobian in the previous. And these are, if you consider the PCIs, are exactly the vector that you have in this direction. And the treatment will give you mg transpose p minus direction because the gravity is usually in minus direction, and then you can find that in this way. If there is any flexibility, if there are some springs somewhere, you add that one to the potential energy as well. So we have a number of joints, so we have the sigma of that, and also we can have the KIs considering being in here. Now, if we have the KP and we have the mass matrix, almost everything is done. We can just put all together. We have the QIs here. The Q is very simple. We have the L, K minus P. We have the kinetic energy, potential energy, and find the derivative. Let me do the derivative not just intuitively. Do it one by one to find some other approach. As you can see, the L is equal to, as you see in here, L K minus P. So this plus P, this comes into the picture. K minus P comes into the picture. So L K minus P will give you 1/2 Q dot square M Q dot plus this value. And if you have this plus value, now you would like to find the derivative. Note that the K is a function of Q and Q dot. But P is a function of Q, only P. You see here, only we have the P either in this case or this case. We don't have any velocity term here. So the potential energy is a function of Q, but kinetic energy is a function of Q and Q dot. Now, if you take the derivative with respect to Q, this comes only the derivative with respect to K. And K with respect, because this doesn't contribute here. And this is very simple. The partial K with respect to Q dot. Partial K with respect to Q dot, this is a quadratic form, will give you MQ Q dot here. So we have mq dot in here, and we should take the derivative of that. This m should be also bold. Should also fix that, bold to mq. So we have a matrix here and q dot here. We find the derivative of that. The one gives you mq q double dot, the mass matrix times the angular velocities, or the second derivative of q's, plus also m dot times q dot. We have two terms coming out from this part. We consider these two terms in here. And from the next part, as you can see, partial L with respect to Q is, we have both of them a function of Q. So the L1 comes here, and L was K minus P. The P1 comes here. And if we have the partial with respect to P, we can define the last term, partial P with respect to Q, as the gravity term, the terms that the gravity will contribute into the system. So we have divided the dynamic equation in a general form, just using the Jacobian and the framework that we have done in here. mq double dot and gq, this is the part that is found before in here, and it's come from the first derivative part, and this comes from the last derivative part of this portion. And we have a large value here, m dot q dot, something terrifying. And partial q with respect to q, we should do a lot of calculation here. Of course, we don't do it by hand, we do it by Maple and MATLAB, but these two parts are very easily found without doing any derivative. You can just simply find this one and finding the partial of this one to this part. We also call this one as the another term, so we have three terms here. We put the three terms in like this: the mass matrix times q double dot, the gravity vector, and this one we call it V. These are the Coriolis and centrifugal vector. The velocity, you remember that the acceleration that we had before in the first slide of this chapter, two terms. We have some omega squared terms or V squared terms that are the centrifugal point, and some V times omega or omega cross V terms that these are the Coriolis term. All of these, let's say, gyroscopic effect or, multiplication terms comes into this part, which makes the problem quite sophisticated and hard. So we can find this and this very easily. This one we should do it by one by making the derivative that we have in here. We can call this derivative find by quite one by one derivative that we have in here. And as we can see also, we can write this vector as a matrix times q dot by just getting some, and this matrix is called the Christoffel matrix. We will find this matrix in a few next session. But now, as we see, now if I just want to give you the 1, 2, 3 form, if we just go very fast what we have done here. First, finding Q and Q's are very easy from the robot. To find a Jacobian, to find the Lagrangian, it is important to find the Jacobians. Which Jacobian? Ji's. And Ji's are found the same as we have done previously, but for the center of mass, considering this vector, not the other vectors, and by considering some sort of exactly like what we have as the screw axis, we have the same axis here for the before values, and then we can find, if we have the Jacobians, then we can find the M matrix quite easily by the Jacobians. The P matrix by just multiplying this one. This is also very easily found. And then we have M and P here. We have M and P. We make the derivative of that. We find the M and the G vector here. And then we go to find the V vector. The V vector is found by this two term, and we call it a Coriolis and centrifugal vector. And this is a dynamic equation of the robot, and it is very, very interesting that for each stereo robot, any type of robot, you have one particular equation. Of course, M, V, and G are different for different robots, but all of robotic manipulator could be represented in this form. And this gives us a lot of freedom to find or define approaches, control approaches to that, calibration approaches, many issues we can find in here. If you don't mind, let me also give one example, because some part of it would be quite clear. If there is any question, please ask your question right now. Again, today we don't see any contribution from you. Jawad is with us. Other people, Zahra is not with us, or usually Zahra, Hussein have some questions. Zahra is not with us. Hussein is with us. He will give the question at the end. No problem. Let me give the example to find everything now by one. We go with two simple examples and one bit more detail. The first example, of course, is the planar elbow, the 2R manipulator, quite simple. And we consider slender bars. You remember, slender bar has 1 over 12 mvm L squared 2 as the moment of inertia. And we consider slender bar here, 2 bars, and I would like to mostly focus on how you find the PCI and the JVIs in here. So we consider that the center of mass is at the half length, A1 half and A2 half. We consider that there are some viscous friction at each joint, and we have also some torques at here and here. So the Q's are simple, theta 1 and theta 2, or 2R. The big Q is tau 1 and tau 2, subtracted also the friction term from them, minus B1 Q dot and B2 Q dot 2. This should be Q dot 1. I'm very sorry, but there is also a mistyping here. I will fix that. As you see, Q dot I, this should be also I. This gives you some sort of friction terms, viscous friction terms. And the moment of inertia is also given by 1 over 12 ml squared. For each joint, there is quite easily found at the center of mass. Of course, if you would like to find from another point, if you would like to find from here, it would be 1/3, but at the center of mass, which we call always center of mass of the interest, it would be 1/12 over that. Now, to find the JVIs and J omegas, we need to find the PCIs. And we go it this way, as you see, very, very intuitively, very step by step for this example. You see, we have PC1, the center of mass here, with respect to 0. So this is quite simple. You know that this is A1/2 of A1, but it has in X and Y direction. So we consider that vector just component-wise. It would be cosine of theta 1 and sine of theta 1. PC1 star with respect to 0 is found like that for the first joint. But for the second joint, we need this one. To do that, I will first find this one and then add this vector. Since we have this vector, the red one, we can enlarge that and have the this vector, just instead of using a1, 1/2 of over a1 divided by 2, we use a1 here. So first find this one, PC2 with respect to 1, the frame 1. PC2 with respect to frame 1, with respect to here, is 1/2 A2, C12 and S12. Consider that everything is considered in this frame, from this frame. So this vector, which we call PC2, this vector up to here, up to 1, PC2, the center of 2 mass, with respect to 1, up to point 1. This vector would be A2/2, C12 and CS12, since we are considering everything in the 0 frame. So we have this vector. Now we add this vector to it. I didn't drive this, but to find this vector, we have this plus this, and this one is A1C1 and A1S1. As simple as that. We have PC1, 0, and PC2, 0. And that's all what we need. Since we have these two, the rest could be found by just manipulation. JV1, as you see, JV1, we have the first column, the second column is 0. So the second column is 0, and we have the first column. And the first column is, you remember, Z cross PC1. We have Z in this direction, cross PC1. You make the cross product in here, and you find minus S1 and C1 here. Just S cross that gives you the direction on the other side. You can find this by using symbolic manipulation, quite easy. Consider that the second column is 0. What about JV2 and omega 2? For JV2 and omega 2, as you see, we have we are using these two other components. First, PC2 with respect to 0. As you see here, PC2 with respect to 0 cross ZI. Z cross that will give you this one. And as you see, and then PC2 with respect to 1 gives you this vector. This is for the final vector, and this gives you this for the second vector. The components are basically this multiplied by this vector, this Z11, Z2 and Z1 here. So the Z1 gives you this one, and Z2 gives you this vector. We have a full vector here because this is a 2 by 2 matrices as well. We have the last part here, the Z1 of, but all of them are equal to 0 because we are in a planar case and we don't use that in our cases. Now we have the JVs and J omegas found. Very simply go to this vector, MI, JVI transpose, JVI, omega I, IC transpose. And this can be done by just simple matrix manipulation. You can find this J matrix as this one. JV1 will contribute in many of these terms, and JV2 and JV1 will contribute into the A1, M1, A1 terms actually. This comes from the first component, and the rest comes from the other component. I have wrote a program to do that. Of course, you can do it by hand, but it is much easier to write a program, and you find the mass matrix very easily. Again, you need 3 vectors, not just these 2. You need 3 vectors, PC1 with respect to 0, PC2 with respect to 1, and PC2 with respect to 0. here you use PC1 with respect to 0 here with PC2 with respect to 0, and here PC2 with respect to 1, and then you can go forward to find that. And these are the z-axis that we have in, as you see in here. You remember we have JW was as the component-wise vector in here. Now that we have found this equation quite well, we go to the next step and find the G vector. What about the G vector? Very simple. We have PC1, we have PC2 with respect to 0. We just multiply M1, and G1 is basically on the other direction. This requires some the G transpose times this. This is also some correction. I will correct it right after the class. So M times this, M G times P, G transpose, and G is in the minus Y direction, and we have minus Y direction, we have minus M GPC1. The result will be given in this form. The G is multiplied by PC1, and also PC2, and you can see that M1 is only multiplied by A1C1, as you see here. M1 A1C1 with half. M2 is multiplied by A2 and A1. Both of them comes into the picture. Very simple manipulation here. And the rest, the final one is the V1. V is difficult. In this case, it's not that difficult. The V1, we should find the derivative of this with respect to M dot Q with respect to time. And you see here, we have the C1, C2 here, only C2 here, as the variable which is with respect to time. So this gives us some time derivatives, and if you find that, you find a term here, and the partial k with respect to q, which this one also contributing to one term in here. If you write these two all together, hopefully for this robot it is not that big difference. Of course, I didn't do it by hand, I do it by MATLAB, and I will provide the MATLAB function to you to find this as well. I will stop in here. The only, again, issue is to find these three variables quite accurately, and if you find that, then the rest can be done just by simple manipulation. Any question now? Any questions? I brought this value here. These are very similar what we have done in here to what P star n, to what we have done here. Instead of P star n, we are using PCI star dot n. I just want to mention one issue that has been changed in the last chapter on the force measurement. Yeah, here. By re-examining the problem, I saw that there is this problem on page 60, the manipulability measure was not given to you rightly, because here, as you see, q dot square is equal x dot, the norm of x dot is equal to mu times q dot, and this direction will give you the direct singular value direction. I gave it to you before 1 over sigma. But this is not true because we have the inverse, Jacobian inverse in here. So this is correct. Just use this correction in here. It becomes much simpler if you just use the direct singular values instead of the inverse singular value. And by this means, basically in the examples also everything has been changed as you see in here. And the force direction has been also considered in here. This is one thing that I would like to mention in this class, and also I have provided the programs to you. You can just go through the programs, especially for F-min-con programs. Here you can see the obstacle avoidance problem, which is quite sophisticated and requires some path planning and also some optimization routine. I give the program here. And the programs are available on the LMS website of the course, and you can just run all of these. Please try to upload and work a bit with that you can use the F-min-con approach for your case. You need this F-min-con problem for your next part of the project, not up to here. You didn't need it, but for the next part you need that. And also I changed these examples here. There is also another small problem here. What we would like to optimize for the singular for redundancy resolution was not mu, it was minus mu. If we would like to get away from singularity, then we need to have larger values for mu, since mu is between 0 and 1. For the last case, I have given plus q mu here, which was not correct. And as you see, if you put it minus mu k in here, and I use the Jacobian of the 2R manipulator here, I just made some modification to get a better result. You can see that for the case of non-singular avoidance, we have very close to singularity in here, but when we just open up the system, the lines, the vectors will becomes quite far from each other, or they're far from the retracted or the singular configuration. Please consider these final values which is uploaded on the system, and here again you can see the problem to the program for the case there. I have also added some programs previously. I will also add some Lagrange programs afterward for you on the same site. This was all I wanted to tell you for today. Please keep following the class and doing the assignment on time to have everything being done quite well. The last thing that I would like also to mention to you is a tentative time for the exam, for our midterm exam. We are here for the next week. For the week after, we have the fourth assignment and project, and we will provide you with the solution. I thought it is better to have the program will be finished on the 22nd of or 12th of May, 22nd of Ordibehesht. Our midterm exam is good to be somehow on this time, on Thursday. This is a tentative program now. Thursday امتحان میان ترم در نظر گرفته شده 30 اردیبهشت ماه باشه. یک کمی دیره در واقع امتحان دیررسیه، به خاطر اینکه یه مقداری برنامه‌های شما و این ارائه تکالیف و اینا هی اکستند شد و به طول انجامید. یک هفته بعد از در واقع تحویل پروژه های شما هست که بتونید فرصت داشته باشید که روی اینها کار کنید و دقیقاً بعد از ماه مبارک رمضان ما عید فطر رو 23 و 24 داریم. هفته بعد از ماه مبارک رمضان پنجشنبه قرار میدیم امتحانو که در واقع ساعات کلاس کمتر گرفته بشه که ما کمتر بتونیم چیز داشته باشیم. So the tentative exam, midterm exam would be on Thursday, on Thursday 20th of May or 30th of Ordibehesht. Thank you very much for joining me, and I wish all of you good luck. Mahdi, you have some question. Go ahead.
Sorry, in that day we have a false detection midterm on that very time. I don't know, can it be
on the same day?
Yes, exactly, 20 May, Thursday.
We can bring it a week forward, but that would be in Eid al-Fitr. I don't know if you are happy to have the exam.
Personally, I have no problem, but I don't know about the class.
Oh my God, this is quite bad. We might change the day, maybe to another day. You know, this is the worst thing to be because making it later than that, it is the final exam, it is not midterm. You know, we are already this is the last week of the class. Any suggestion for any time?
Personally, I don't have any classes on Wednesday or Friday. It can be that week if it doesn't need to be more late.
Yeah, it might be possible to do it on Wednesday. Anybody has some problem with Wednesday? Wednesday? No problem on Wednesday? We will leave it for the next class to just discuss about it again. Wednesday 29th for the exam. All right. Thank you very much for being with me. Today was a bit longer than usual, but please copy the new version of chapter 4, and also I will clean up the chapter 5 and will provide you with some some corrected version of the chapter 5 slide. Thank you very much and have a good day. Bye.